If you ask a large language model to describe a coffee cup, it knows exactly what to say. It knows the exact shape, the purpose, and that it holds liquid, all because it has processed millions of sentences written about them. But that same model has absolutely no idea what gravity feels like. It has never experienced the friction of a ceramic handle or accidentally knocked one over on a cluttered desk. For all its vast intelligence, artificial intelligence has spent its entire lifespan locked inside server racks, confined strictly behind glass screens and text boxes. It has zero capacity to interact with the physical world. That confinement is ending. Software is actively stepping out of those servers and taking physical form. This is known as embodied AI. It takes advanced neural networks and gives them hardware, hands, mobility, and sensors, granting them actual situational awareness within human spaces. This bridges the gap between digital intelligence and physical reality. We are transitioning from technology that we chat with to technology that manipulates the physical environment alongside us. Moving through physical space requires a completely different processing logic than generating text. As you can see in this animated diagram, a standard word model navigates a text generation tree. Its entire job is calculating probabilities, highlighting a single path to predict the next logical word in a sequence. That mechanism builds a highly capable conversationalist, but it is completely useless for physical navigation. To move, embodied AI requires an architecture engineers call a world model. Instead of predicting the next word, this architecture runs real-time simulations to predict physical outcomes. It instantly calculates the spatial geometry of an environment, measuring mass and predicting exactly how much friction will occur upon impact. It even maintains object permanence, understanding that an item still exists and retains its physical properties even when it rolls behind an obstacle and out of sensor range. Before the machine moves a single joint, it is already actively simulating and navigating the laws of physics. Taking those physics simulations and executing them in the real world has driven the development of bipedal humanoids. The bipedal design is highly intentional. If these machines are going to operate in our factories and living rooms, they need to navigate spaces scaled specifically for human proportions. That human scale extends to their hands through a capability called microdexterity, which uses advanced haptic sensors to replicate human-like touch sensitivity. These sensors allow a heavy robotic hand to apply exactly enough pressure to grip a delicate egg without crushing it. Fractions of a second later, that same hand can adapt its grip to apply massive torque to a rusted wrench. By combining real-time physics models with sensitive haptic hardware, rigid machines become highly adaptable agents capable of executing highly nuanced physical tasks. This adaptability sets them apart from the legacy industrial robots you find on traditional assembly lines. Those older systems operate on rigid, pre-programmed loops. If an unexpected physical obstacle blocks their path, they freeze or break down entirely. Embodied AI adapts on the fly. If a box falls in its way, it instantly recalculates, steps over it, or routes around the blockage without a human writing new code. We are already seeing this dynamic rollout in extreme environments, like navigating disaster zones or inspecting radioactive facilities where human survival is impossible. The next target is domestic deployment. Humanoid assistants are being developed to bridge massive labor shortages, specifically to help with mobility and meal preparation in elder care. The utility of these machines relies entirely on their ability to leave the safety of a controlled factory floor and function in the chaotic, unpredictable environments of our daily lives. Giving artificial intelligence an independent physical body introduces an entirely new category of risk. In a purely digital space, a software bug in a chatbot yields a typo, or at worst, a nonsensical paragraph of text. This split-screen graphic shows the contrast. On the left, a digital error is harmless, but on the right, a software bug occurring inside a 150-pound bipedal robot operating in a family home carries severe, immediate physical risks. Deploying physical agency at this scale requires engineers and regulators to develop standardized safety protocols and strict liability frameworks immediately. Beyond physical safety, we face the societal consequence of rapidly integrating physical AI into the workforce and the looming challenge of mass labor displacement. As these machines take over manual tasks, society has yet to resolve how it will navigate an equitable economic transition for replaced human workers. We have moved past building smart software designed to generate text and images. We are now engineering physical partners. Think about how your day-to-day existence will adapt. Your relationship with technology is moving from a device you type into on a screen to an entity that physically walks beside you.